every regression line goes through x bar, y bar for different y bars, right? So x1 to xn is fixed, but every time we give those numbers to Tyche, we get a different y1 and yn, and hence a different regression line. So the variance of the regression line is smallest when x is x bar, and it becomes greater as x gets further from x bar, as you can see from the formula for the variance. So similar to our proof that beta 1 hat in lecture 34, similar to how we showed that this for beta 1 hat, y hat minus its expectation, which is expectation of y given x, over the standard error, is a t distribution with n minus 2 degrees of freedom. The proof is pretty much exactly the same, and y hat plus or minus t n minus 2.025 standard error is a 95% CI for the Tyche line. So today we're going to do a number of things. We're going to talk about a prediction interval for a new response, yn plus 1. We're going to talk about the decomposition of the total sum of squares. TSS is RSS plus MSS. And we'll talk about the F statistic for regression. This is not discussed in Rice. We'll also talk about the coefficient of determination. So the prediction interval for response of a new observation is the next topic. And given x1 to xn, we know that y1 to yn, but what if we have a new observation, xn plus 1? We'd like a prediction interval for the random variable yn plus 1. So the prediction interval is the Bayesian analog of a confidence interval. So we have confidence interval for a parameter like a mean, and we have prediction interval for a random variable. Now, based on our regression line, we predict that the regression, our predicted y value is, or y hat n plus 1 would be beta 0 hat plus beta 1 hat xn plus 1. So this is independent of our new response variable yn plus 1. Since y1 to yn are independent of yn plus 1, right? So hence the variance of the residual yn plus 1 minus y hat n plus 1, the variance would distribute, and we know the variance of yn plus 1 is just sigma squared, and the variance of y hat n plus 1 is the formula that we saw above for the variance of the regression line. So in here in this formula, x bar is for x1 to xn, and then we have our x is now xn plus 1. Okay, so sigma squared, and that's sigma squared 1 plus 1 over n plus xn plus 1 minus x bar quantity squared over n variance of x. So furthermore, the expectation of the residual, so that's just the expectation of n plus 1 minus the expectation of y hat n plus 1, and the expectation of y hat n plus 1. Y hat n plus 1 is a unbiased predictor for the point on the Tyche line, which is beta 0 plus beta 1 xn plus 1, and that's just the expectation of yn plus 1. Technically, given x is xn plus 1, but I'm not going to write that. So this is just 0. And so we have that the residual is a normal random variable with mean 0 and variance sigma squared 1 plus 1 over n plus xn plus 1 minus x bar squared over n variance x. And similar to our proof for beta 1 hat, the residual minus 0 over the standard error is a t distribution with n minus 2 degrees of freedom. So y hat n plus 1 plus or minus the t distribution 0.025 sigma squared and square root of 1 plus 1 over n xn plus 1 minus x bar squared over n variance x is a 95% prediction interval for the random variable yn plus 1. Again, a prediction interval because our new response yn plus 1 is a random variable. So a picture of this, there's a 95% chance that the point in red, yn plus 1, is between the purple curve here for a given xn plus 1. Okay, we're next going to talk about the decomposition of the total sum of squares. From homework 9I, you showed that the TSS is RSS plus MSS, so that's the total sum of squares is the residual sum of squares plus the model sum of squares. And so just like in ANOVA, this gives us a decomposition of variability of the total variability of the y's in terms of a residual of the residual sum of squares and what's also called the model sum of squares, which is in this picture here. You can see it. The distance from yi to y bar, you can decompose that as the residual plus the model, but more is true. In fact, the sum of squares of the residuals and the sum of squares of the model give you the total sum of squares. But more is true. The RSS and the MSS are independent. So to see this, let's remember our geometric approach. So here we have, we're in our statistical model for the simple linear case here. So y, x, beta hat, y hat, y bar, e hat. These are all vectors as shown. And we have, in this case, k is 1. So we have at least 2 observations, so n is greater than or equal to 1 plus 1. And y, so y is sticking outside of the column space for x. And so the y hat is that point such that it's the orthogonal projection of y onto the column space. That defines the beta hat such that the Euclidean norm of the residual is as small as possible. So the residuals are orthogonal to the column space of x and hence orthogonal to y hat, which lies in the column space of x. Now we know that x bar, y bar lies in the regression line. When we plug in x bar into x, we get out y hat. So y hat lives in the column space of x and is orthogonal to the residual. So what this means is that y hat minus y bar is orthogonal to the residual. And since the joint y minus y hat minus y bar is a bivariate normal vector, orthogonal vectors are independent vectors. So it follows that the random variables RSS and MSS are independent. So now from lecture 34, we know that RSS over sigma squared is a chi squared with n minus 2 degrees of freedom. And since y1 to yn are independent normals with variance sigma squared, it further follows that yi minus y bar is over sigma is normal, and in particular the TSS over sigma squared is a chi-squared with n minus 1 degrees of freedom. So that was shown in chapter 6 and something we've used before. So it follows that the MSS, which is the TSS minus RSS, or TSS, so the MSS is going to be chi-squared with n minus 1 minus n minus 2, which is just 1 degree of freedom. So next we're going to talk about the F statistic for simple linear regression. So we wish to test whether our predictor and our response variables are independent. In other words, whether beta 1 is 0 or not. So that's the null. The alternative is that it's not 0. And so here's a picture. So in this picture here, we have the regression line. And you can see that when the null is true, then when the null is true, then the MSS would be very small, right? Because the MSS is the distance from the regression to the mean. If beta 1 is 0, then that would mean that the regression line would coincide with y hat. So now remember, the definition of an F distribution is a ratio of chi-squares over their degrees of freedom. So we have here for simple linear regression an F1 n minus 2 F. And we reject the null when this is large. So not surprisingly, this is equivalent to a T distribution with n minus 2 degrees of freedom, so squared, just as in ANOVA. So finally, we're going to talk about the R squared, the coefficient of determination. So in homework 9H.B, so you showed that that sigma squared residual is 1 minus R squared sigma squared y, where these are defined as shown here. What this basically gives us is that the RSS is 1 minus R squared TSS, or that the R squared is MSS over TSS. And R squared is called capital R squared in multiple regression. And it has the interpretation that it's the fraction of the total variation of y explained by your model. If MSS is very small, the slope of the regression line is small, and R squared is close to 0. If MSS is TSS, then your regression line is a perfect straight line. Your data lies on a straight line. I should say the data lies on a straight line. In other words, R squared is 1. So in general, RSS decreases or remains the same as we add more predictors to the model, but we'll talk about this later. So I finally just ended with a note that you can think of ANOVA as a special case of regression if you make your x's the treatments. So x is supposed to be a continuous random variable, but if you just say, okay, I'm going to think of it as a discrete. So I have treatment 1, treatment 2, treatment 3, and then I have different y's for these treatments. I've circled the mean of each treatment group, and the regression line is the best fitting line through our data, and that roughly coincides with the line through the means. In ANOVA, our null is that the treatment groups all have the same mean, and in regression, our null is that the slope of the regression line is 0, and those correspond, right? Because if the means are all the same, then the line is horizontal, and if the line is horizontal, the slope of the regression line would be 0. Okay, guys, have a great day. I'll see you next time.